name is Nur Natasha Amira binti Mak Nasir and my metric number is AIM 2041. Now I will do the explanation for the activity 1, which is electrical power measurement in a DC circuit. Now I will make a circuit connection for power measurement in DC circuit in Proteus software. Okay, now I will make this circuit connection in Proteus software. Firstly, we need to choose DC source, and we choose this V source as a battery source in this connection. And then we choose virtual instruments mode to choose DC voltmeter, DC ammeter, wattmeter, resistor. You choose any resistor, okay, and then we rotate it like mirror. And then we need to change this in watt. And then we connect this all together. So the connection for the circuit is complete, and then we need to fill the V source with 60 volt as in the questions. So the resistor is the only we need to change the value to get the simulated voltage, ampere and wattmeter. After that, we need to change the value of the resistor from 100 to 500 ohm to get the simulated voltage, simulated current and simulated power. Okay, so the value of the resistor we change to 100 ohm, and then we run the simulation. Okay, so we get the simulated voltage is 60 volt, simulated current is 0.6 ampere and simulated power is 36 watt. And then we change the value of the resistor with the 200 ohm, and then we run the simulation. After we run the simulation, we get the simulated voltage is 60 volt, simulated current 0.3 ampere and simulated power is 18 watt. After that, we change the value of the resistor with 300 ohm, and then we run the simulation. After we run the simulation, the voltage we still get 60 volt, simulated current is 0.2 ampere and simulated power is 12 watt. Okay, so the fourth time we change the value of the resistor with 400 ohm, and then we run the simulation. And then after we run the simulation, we get the simulated voltage is 60 volt, simulated current 0.15 ampere and simulated power 9 watt. Lastly, we change the value of the resistor with 500 ohm, and then we run the simulation. After we run the simulation, we still get the simulated voltage is 60 volt, simulated current 0.12 ampere and simulated power is 7.2 watt. After that, we need to calculate the DC power using equation 3 and then compare the calculated power with the simulated power. So the formula is P cal equal to simulated current times simulated voltage. So this is the manual calculation for the calculated power. The value from the manual calculation we obtained was exactly the same with the simulated power. This is the calculated power, and this is the results. It is totally the same. This means the value simulated is same with the theoretical concept and have no difference between it and not being disturbed by any problem that can cause slightly error for this value. Lastly, the calculated power was calculated again with the 3% error on it. We need to find the 3% error, and then we add back to the original value. For 36 watt power, the error is 1.08. For 18 watt power, the error is 0.54 watt. For the 12 watt power, the error is 0.36 watt. And for the 9 watt power is 0.27 watt. Lastly, for a power of 7.2 watt, the error is 0.22 watt. This result shows the higher the value of calculated power, the higher the error that can be obtained to the result.
Hi, greetings to Dr. Afiza. My name is Pravindra son of Kannan. My matrix number ID is CE210 and 202. So today I want to do circuit for number 3 and activity 3. So first of all, I need to add the AC voltage, AC source. After AC source, I want to add AC voltmeter to calculate the AC voltmeter. After that, I want to add resistance. I flip it first, then capacitor, and for calculate the apparent power and real power, we need to add the wattmeter. So I want to change the value first. This is 100 watt and 50 hertz. and this one I want to change to MVA to VA, and this one change to watt, and also the resistance R1 change to RL, R load, and the value of the resistor is 100 ohm, and same for to the capacitor. The value of capacitor is 2UF. So that's all, we're done for the value all. Now just connect the circuit. The positive, go to positive, and this one connect to here because the current one, and then this one go to the RL. I just drag the RL, okay, and then the positive connect here, and same goes here, this positive connect here. After that RL connect to the C, and here the negative one, negative connect to the negative, and same go to here, and also for the AC voltmeter, positive connect to positive, negative connect to negative to measure the AC source. So that's all for the circuit. Now just simulate the circuit and pause. So this is 70.7 volt AC volts from the AC source, and the VA is 3.14 and 0.20 for value capacitor 2UF. And now we want to continue for the stop first. Now we have to continue to 4 microfarad capacitor value, and let's see the changes. So just run and pause. The AC volt is same as we know, and the VA apparent power is 6.23 and the real power is 0.77. So we can see the apparent power and real power are increasing due to the capacitor. Let's stop and change the capacitor value from 4 to 6 microfarad, and then run and pause. So same to 6 microfarad, the apparent power and real power value are increasing. So now let's change the 6 microfarad to 8 and simulate. Now the apparent power and real power are 12.1 volt and 2.96. They are increasing. Now for 10 microfarad, the last one, I simulate and pause. So now the VA is 14.9 and the real power is 4.45 for 10 microfarad capacitor. So from the simulation we done, I can conclude while the value of the capacitor is increased, the real power and apparent power also increase. That's all. Thank you.
Hello everyone, my name is Vishwaran Araki Murugan. My matrix card number is AE190089. Today I'm going to explain you all about for activity 2 for the electrical power measurement in an AC circuit with a resistive load. So with the given example of circuit, we are going to simulate it in a Proteus. For the first case, since we are using an AC voltage source, so we can go to the component, libraries, and we can find a component as V sign which indicates the sinusoidal wave for AC voltage source, and we can use it, and for our case we are using it. And for the next case, since we are going to calculate the RMS voltage of an AC source, we need a AC voltmeter. So we can search for the AC voltmeter under the virtual instruments mode. This shows an AC voltmeter. And to measure the power, for our case we are going to measure the real power. So we need an wattmeter. Under the same virtual instrument mode, we can find an wattmeter. This is a wattmeter. So for last but not least, since this is only a resistive load circuit, we are going to use an resistor. And for the resistor, we can go to the component part from the libraries and search for a resistor. This is an example of resistor, and the resistor we are using for our current simulation. And since we have, for the next part is the connection part. The ammeter, we are going to connect it parallel to the voltage source to find the RMS value, and the load is connected to the wattmeter and the AC voltage source. So for the terminal part, the positive terminal is connected to the positive terminal of the load, and for the negative terminal we are connecting straight to the voltage source. And since this shows the current moving flow, it is moving down, the input current is connected at this terminal, and the output current we are connecting it directly towards to the positive terminal of the load. And now for the values part, since the given value is 100 voltage for the peak, we are going to change only the amplitude, and the given frequency is 50 Hz. And for the wattmeter, since we are going to measure the real power, we make sure the output is in watts. And now we have chosen the watt, and we are going to label it as real power. Last but not least, we are going to change the value of the resistance to 100 ohm. And now we can run the program. So for the first case, we are getting a VRMS force of the voltage source as 70.7 voltage, and the real power for the 100 ohm resistor is the 50 watts. For our next case, we are just going to maintain the arrangement and going to change the value of the resistance only. This time we are going to use 200 ohm. And again run the program, and we will get the same VRMS, which is 70.7 volts, and the real power is slightly reduced to 25 watts. For the next case, we are going to use a value of 300 ohm. And we run the program, and the VRMS remains the same as 70.7 volts, and the real power is 16.7 watts. For the next case, we are going to change it, the resistive load, to 400 ohm. and run the program again, and VRMS is still the same 70.7 voltage, and the real power is 12.5 watts. Last but not least, we are going to use an resistive load of 500 ohm, and run the program. We will get the same voltage, which is 70.7 for VRMS, and the real power is 10 watts only. So once we finish the simulation, we tabulated the values in the table, and using the formula for the calculated real power, we done the manual calculation, and the conclusion was all the calculated real power is almost similar to the simulated power. So from this experiment, I can conclude that as the resistance RL load increases, thus the calculated real power or the simulated power will reduce. That's all from me. Thank you.
Greetings to Dr. Hafiza. My name is Shankar Nalaki Subramanian, matrix ID AE190090. So I'll be presenting for activity 4 for experiment 6. This is the circuit that we are required to simulate. We have a voltmeter in parallel, a wattmeter, a resistor, and an inductor. The resistor has been kept at 100 ohms throughout the simulation. And the inductor has been increasing from 0.002 to 0.01 Henry. So in order to simulate this diagram, what we need is a AC voltage source. So we can use this sine wave AC voltage source. Put it here. And to measure this voltage, we can use a AC voltmeter. It must be AC lah. It cannot be DC voltmeter. And can use a wattmeter to measure the power, apparent power, and also the real power. And finally, our components, which is the resistor. So we'll be using a generic resistor. Let's rotate this. And we can use an inductor. So I'm just going to use a generic inductor.
So let's rotate this.
So you know that the resistor has always been set to 100 ohms. So we just keep it at 100. And the resistor, and the inductance is 0.002. So this is for the first part of the simulation, and the voltage is 100 volt peak. So the amplitude, the highest should be 100, and the frequency is at 50 hertz. So I've chosen to use 2 wattmeter, a slight modification in order to make the experiment more easy to understand for the viewers. So let's connect the circuit. So what I'm doing now is I'm connecting the current. So the wattmeter reads current. This is where the input current and this is the output current. So this part of the wattmeter measures the ampere. And this is the input voltage and this is the output voltage. So this part will measure the voltage. As you can see here, if you notice, if I connect it like this, it will be parallel to this line. So it's very easy to use the wattmeter, and this would be in series, and this would be in parallel. So we are done with the input voltage. Now we should handle the output, and this would be in parallel as well. So that's all. This is set to watts. This is set to volt ampere. So this measures the apparent power, and this, however, measures the real power. So let's run the simulation. So first off, we can see that when we input the input voltage amplitude around 100, the voltage reading here shows around 70.7 AC volts. So what this means is this is actually the VRMS of the input graph, of the input voltage graph. So the root mean square value, which is 100 divided by square root 2, we will get 70.7. So that's why it's here. And this is the apparent power, 50 volt ampere, and the real power is 50 watts. So now let's increase the inductance to 4. So when we increase the inductance, from this experiment, we did not notice any significant change. The the apparent power and the real power is at 50. This doesn't change now because this is influenced by the input voltage. So let's stop the simulation. Now let's increase it to 0.06 Henry. Now let's run the simulation. The simulation, we still get 50 volt ampere and also 50 watts. Now let's increase the value to 8. So when we increase the inductance, we still get 50 volt ampere and 50 watts. And finally, 0.01 Henry. 0.01 Henry. Now let's run the simulation. Here, when we increase the inductance to 0.01 Henry, the apparent power is around 50, but the real power is dropped to 49.9. So when we calculate the power factor, the efficiency for this graph, for this circuit, the power factor is higher, meaning it has a better efficiency compared to the others. So this could be dependent on the current, because the inductors, it controls the current and capacitor controls the voltage. So the higher inductance, meaning a longer time for it to charge. So this could play the role in the circuit, in the circuit's efficiency. So that's all from me. Thank you.